This is a Chemical Kinetics podcast in which the importance of chemical timescales in modeling will be discussed. Chemical timescales are important for gaining insight into a total combustion process. For example, if the chemical timescale is fast compared to diffusion processes, the chemical process goes to completion, meaning equilibrium, before it diffuses very far. This has an important implications for modeling, meaning the chemistry can be simplified if the chemical processes are very fast with respect to all other processes, such as mixing, diffusion, or turbulence. On a computational level, varying timescales of different processes allow simplifying assumptions to be made. For example, fast chemical timescales allow that less detail need be known for processes or reactants and complete combustion products. At high temperature, the timescales can be fast with regard to the transport processes. The consequence is that the kinetics can be considered as either burnt or unburnt, meaning that intermediate chemistry does not play an important role. A challenge now for chemical kinetics is lower temperatures. Not only are these processes important, but the chemical processes are of the same order of magnitude as other processes, such as transport. They are difficult to simplify, and the mixing of intermediate states dominates. How is the chemical timescale quantified? Of course, the chemical timescale is directly influenced by the chemical rate constant. The higher the rate constant, the faster the process, and thus the smaller chemical timescale, so there must be an inverse relationship. However, for the first order reaction, the reaction decays exponentially, but it still takes an infinite amount of time to reach zero, so this is not a useful measure. Since the timescale is a relative concept, it is not entirely important exactly what we decide. By convention, this is also used in electronics, the timescale is set to the point at which the concentration is 1 over E of the original. How much time is needed to consume 63% of the original substance? Solving the original first-order equation, we find that first-order chemical timescale is actually the inverse of the rate constant.